So in the third activity of this lesson, we mentioned that yesterday or in the previous lesson, we discussed systems of linear and quadratic equations. And today we're going to apply these concepts to systems of two quadratic equations. In problem 1, we're asked to consider these two quadratics, and we're going to use the substitution method, same thing we used with the linear quadratic system to solve it algebraically. So if they're both equal to y, then we can say they're both equal to one another. We would prefer a positive a value. So let's take everything from the right side of the equation and move it over to the left so that our quadratic equals 0. And then we can use all of the algebraic techniques that we're familiar with. So I would add x squared to both sides, subtract 10x, and add 1. And then I would have the quadratic 2x squared minus 7x minus 4 equals 0. So at this stage, I have a choice. I can try to factor it, or if I'm more comfortable with the quadratic formula, oftentimes when I have an a value, the factoring process is a little tougher, so I would probably go right to the quadratic formula. I have an a of 2, a b of -7, and a c of -4. Plugging everything into the quadratic formula, I end up with my two answers, -1/2 and 4. Those would be my two x values. And I know that I'm looking for both x and y values because if we were to graph this, we know that the solution would be the intersection of these two parabolas. And since I have two x values, there are two associated y values with them. So I'm going to take each one and individually plug them into either of these two equations would work. Probably going to do the first one since it has a positive a value. So putting -1/2 in place of x in both places and simplifying with the help of a calculator, I get y equals -25/4. And then I do the same thing with the other x value. So my point is -1/2 in the x direction, -25/4 in the y direction. That's my first point. So then going back to my other point, 4, plug that in, same place as I did the first time. And then simplifying with the use of a calculator, I get 23. So my point is 423. So these are the locations on the graph of where these two parabolas would hit one another if I did it correctly. All right, so let's check it out. Question 1b, solve it graphically. So let's take a look at our trusty Desmos calculator. So I have them both entered here. Let's pull them up on the graph. And as I expected, I have 2 points of intersection. And we have this guy down here, -1/2 and -6.25, which would be the decimal equivalent to 25/4. And then here I have the point 423. All right, so pulling that up on the graph in my workbook, you can take a quick sketch of that. So what did I notice about my two answers? When I did algebraically and I did it graphically, as expected, I found that the solutions were the same. Okay, so I'm asked next to think about the graphs of two quadratics. So you've got a couple parabolas on a graph, and let's describe the different ways in which they could intersect and provide a sketch for each case. So the first possibility, there is always the possibility that they won't intersect. Could be that they actually intersect but only in one location. We would say that these two parabolas are tangent to one another, meaning they touch at only one point. There's the case that we just discussed where there was two distinct locations where they intersected. And then there's actually a fourth possibility that they could actually be the same graph, just a little bit different version of the same quadratic function. It could be coincident, meaning every point on one graph was actually the exact same as every point on the other. And in that case, there would be infinitely many solutions to the system.